Welcome to the video for the second derivative test. It turns out that we have an additional test for extreme values besides just the first derivative test. Here we'll formally give you the second derivative test. We'll talk a little more deeply about it. This says let f prime and f double prime exist at every point in an open interval from a up to b containing c, and suppose f prime of c equals 0. Well, without using the words, they just told us C is a critical point. That's what that notation is telling us. The second derivative test says if the second derivative is negative, then again, plugging the critical point into the function is a local maximum. And if the second derivative is positive, plugging that critical point into the function, not into the first derivative, not into the second derivative, but into the function itself, that output value is a local minimum. Well, let's see why that's true. If the second derivative, at some point, we're going to say the critical point, is negative, then our function f, when our second derivative is negative, we learned on our concavity lesson that our function f is concave down. Well, concave down says we have a maximum. If we're concave down and we have identified where f prime equals 0, we've identified a critical point, so we know the slope of the tangent line, slope is 0, then we know that we have a critical point, and we could have either a max or a min. If we find out that our function is concave down, we know we have a maximum. That's what this is saying. If we find out, or can confirm, that our second derivative is positive, we know our function f is concave up. And the second derivative test says we already know this is a true statement. So we have a critical point. We have a horizontal tangent line. Horizontal tangent line. First derivative is 0. So we have a critical point in C. And if f is concave up, then our function has a minimum at that critical point. So this says f of C is a max. This says f of c is a min. That's what the second derivative tells us about our original function. So whereas the first derivative uses concavity to determine whether a max or a min is occurring, the second derivative test uses concavity to determine the same thing. So we don't necessarily have to look at a graph. We can do it analytically as well, and we'll do an example here in a minute. But here's the second derivative test in a nutshell. If c is a critical number or a critical point of f prime, and f double prime at that critical point, this is not f double prime at some random place. We're plugging that critical point into our second derivative function and looking at the SIGN sign that is the result. If that result is positive, then the point c, f of c, plugging the critical point into the function, will be a relative minimum. If we take that critical point, plug it into our second derivative, and we get a negative sign as a result, then the point c, f of c is a relative max. But here's the kicker to the second derivative test. If we plug that critical point into our second derivative and we get 0 or undefined as a result, then we got to pick another test. The second derivative test can fail. The first derivative test cannot. But the second derivative test can fail. If it fails, we've got to fall back on the option that we know will work for us, and that's the first derivative test. Here is an example of where the first derivative would equal 0, horizontal tangent line, f prime, we'll call that a critical point, equals 0. But in this case, look again, we're increasing and we're concave down, and then we go still increasing but concave up. In this case, that is an example of where the second derivative test fails. Second derivative test fails. Okay? We don't have a max or a min there. And we would see if we ran the first derivative test, our first derivative would go from positive to 0 to positive. So we would not have an extreme value there. Okay, but that's not to say that we would never have an extreme value when the second derivative test fails. Here's another counterexample. This quartic function. It is true here that at this value, f prime, we'll call it a critical point, at c equals 0. It is true as well, because of the flatness here of the quartic function at that minimum value, it turns out the second derivative is 0 as well. But our first derivative, our slopes go from negative to positive. So this is a counterexample where the second derivative test fails. Here again, second derivative test fails, but we do have an extreme value. And this is the point in the derivative test work where I have students decide, well, if that's the case, if the first derivative test always works and the second derivative test could fail, I'm not going to bother to learn the second derivative test. Here's the problem with that thinking. Sometimes on the AP test, you're not given information about your first derivative. Sometimes the only information you're given is about your second derivative. And this is some function, some ugly mess, or some theoretical mess that you can't find the first derivative or the second derivative of. And they'll do that. They'll do that on theory questions. But they'll give you information about your second derivative sometimes in the setup of the problem. Then they'll ask you about extreme values. And they force you to use the second derivative test. So you can't throw this test under the bus. You've got to know this test. All right, so let's do an analytic example. For f of x equals 1/3 x cubed minus x squared minus 3x plus 4, use the second derivative test to identify local extrema. Well, let's see what that process looks like. Step number 1, in order for me to get to the second derivative and see what the sign is at some critical value, I got to find the critical value. Critical values happen where f prime equals 0 or is undefined. Again, f of x is a smooth continuous polynomial function. It's defined everywhere. So I want to find where the first derivative equals 0. So I'm going to take the derivative of f, 3 pops down front, reduce the power by 1. Power pops down front, reduce the power by 1, right? So there's my derivative function. I want to know where it equals 0 because I'm on the hunt for plugging my critical point into my second derivative. I've got to identify my critical points. That's where the first derivative equals 0 in this case. So I have a quadratic function. I'm going to find the two factors. I know that's the case. I have more negative here than positive, so I know those are my signs. And therefore, x plus 1 equals 0 when x is negative 1. X minus 3 equals 0 when x is 3. There are my two critical points. So I need to see the sign of my second derivative at negative 1 and the sign of my second derivative at 3. So the next step in the process is to find the second derivative function. So now I need f double prime of x. That is 2x minus 2. So 2 times negative 1 minus 2, that gives me a negative. And 2 times positive 3 minus 2 gives me a positive. And according to the second derivative test, this means f is concave down, right? Which means f has a max at negative 1. This means f is concave up. That's what concave up looks like. So that means I have a min. Now, students don't like negative and max paired and positive and min paired, but if you'll keep concavity in mind, you shouldn't struggle with that. So identify local extrema. F of -1, and I'm going to leave space there and we'll go back up and figure out what that value is a local maximum. Because the second derivative is negative there, concave down, I have a maximum. F of 3, notice I'm plugging my critical points back into my original function because that's where the extrema, or what the extrema are. So whatever that value is a local minimum. All right? Because second derivative is positive, function is concave up, that's a minimum. All right, so plugging -1, I have 1/3 -1 cubed minus -1 squared minus 3 times -1 plus 4. All right, so -1/3 minus 1 plus 3 plus 4, that's some fraction, -4/3 plus 7, what is that, 21/3. So I'm going with 17/3. We'll try that. 17/3. We'll see if I'm right about that. Then we're going to plug in 3. 1/3, 3 cubed minus 3 squared minus 3 times 3 plus 4. That's going to cancel with one of those. That's 9 minus 9. Those are gone. Negative 3 times 3 is 9 plus 4. So if I did all that work right, I'm not sure I did, I have a local min of -5. There is the process for running the second derivative test. So make sure analytically you could do that. Find the extrema of f of x equals 2 sine x plus cosine 2x on the open interval from 0 to 2 pi. So let's remember what our process was. Our process was find the first derivative function. 2 pops out front. The derivative of sine is positive cosine, plus, this is a chain rule problem, the derivative of the outside, not changing the inside, times the derivative of what's inside. So there's our first derivative, 2 cosine x minus 2 sine of 2x. We need to know where that equals 0 or is undefined. Shouldn't be undefined anywhere. Those are two smooth and continuous functions, one being subtracted from the other. Shouldn't be undefined anywhere. This is a case where we're going to need to use that trig identity substitution. Hopefully you remember it. I told you that's the one trig substitution that we'll see most often besides the Pythagorean identity. The sine of 2x is equivalent to 2 times the sine of cosine x, or sine of x times cosine x. I've just made that trig substitution. So we'll clean that up. 2 cosine x minus 4 sine x cosine x equals 0. Looks like I'm about out of time. Why don't we pick up right there on the next video? There'll be one more video for the second derivative test.